Welcome to today's exploration of one of organic chemistry's most fascinating molecules. We're diving deep into the world of benzene, the foundation of aromatic chemistry. At the heart of our discussion is the molecular formula, C6H6, 6 carbon atoms and 6 hydrogen atoms, perfectly arranged in nature's most elegant ring structure. Benzene represents the simplest aromatic hydrocarbon, but don't let its simplicity fool you. This remarkable molecule possesses unique characteristics that set it apart from ordinary hydrocarbons. Observe the beautiful hexagonal structure before you. 6 carbon atoms form a perfect ring, each bonded to a single hydrogen atom. But here's where it gets interesting. Notice the circle in the center of the ring. This isn't just decorative. It represents something extraordinary, a delocalized ring of pi electrons. Unlike traditional double bonds that stay fixed between two atoms, these pi electrons are free to move around the entire ring structure, creating what chemists call a delocalized electron cloud. This electron delocalization is the secret behind benzene's remarkable stability. Let's define benzene precisely. Benzene, with the molecular formula C6H6, is the simplest aromatic hydrocarbon characterized by a delocalized ring of pi electrons. This definition encapsulates everything that makes benzene special: its aromatic nature, its ring structure, and those crucial delocalized electrons that give it extraordinary properties. Now, let's examine the 5 fundamental properties that define benzene's character. Number 1, molecular formula. C6H6, 6 carbons, 6 hydrogens. This simple formula represents a complex and beautiful arrangement. Number 2, stability through resonance. Benzene doesn't exist as alternating single and double bonds. Instead, it exists as a resonance hybrid, a perfect blend of multiple contributing structures. This resonance stabilization energy is approximately 36 kilocalories per mole, making benzene exceptionally stable and resistant to addition reactions that would break its aromatic system. Number 3, sp2 hybridization. Every carbon atom in benzene is sp2 hybridized. This means each carbon forms 3 sigma bonds, 2 with neighboring carbons and 1 with a hydrogen atom. The remaining unhybridized p orbital on each carbon overlaps sideways with its neighbors, creating that continuous pi electron cloud above and below the ring plane. Number 4, planar hexagonal geometry. Benzene is perfectly flat, a planar molecule with precise 120-degree bond angles. This geometry isn't accidental. It's the optimal arrangement that allows maximum overlap of the p orbitals, essential for maintaining the delocalized pi system. All 12 atoms, 6 carbons and 6 hydrogens, lie in the same plane. Number 5, uniform bond length. Here's a remarkable fact. All carbon-carbon bonds in benzene measure exactly 1.39 angstroms. This is neither a typical single bond, which is 1.54 angstroms, nor a typical double bond, which is 1.34 angstroms, but perfectly intermediate. This uniformity is direct experimental, proof of electron delocalization. All bonds are identical, each having partial double bond character. Why does benzene matter? Because benzene is the gateway to understanding aromatic chemistry, a cornerstone of organic chemistry that explains the behavior of countless molecules. From pharmaceuticals to plastics, from dyes to DNA bases, the principles we see in benzene: resonance, delocalization, aromatic stability. These concepts ripple throughout chemistry, helping us understand and predict the behavior of complex molecular systems. Story of benzene structural models and their historical evolution. Our timeline begins in 1825 with Michael Faraday. While studying oil gas, Faraday isolated a new hydrocarbon. He determined its empirical formula was CH, but he did not propose a specific structure. At this stage, benzene was simply a discovery, a mysterious liquid with a unique composition, represented here by a simple hexagon, waiting for its true identity to be revealed. Fast forward 40 years to 1865, when August Hückel proposed a revolutionary idea. He suggested that benzene consists of a ring of 6 carbon atoms with alternating single and double bonds. This was a groundbreaking moment in organic chemistry. However, Hückel's model had a problem. If benzene truly had alternating double and single bonds, it should behave like an alkene, undergoing addition reactions easily. But benzene was surprisingly stable and unreactive. To explain this, Hückel later proposed that the molecule oscillates rapidly between two different structures, shifting the positions of the double bonds. While this was a clever attempt to explain the symmetry, it still didn't fully capture the true nature of the molecule. The final piece of the puzzle came in 1931 with Linus Pauling. Using the emerging principles of quantum mechanics, Pauling introduced the concept of resonance. He explained that benzene does not flip back and forth between two structures. Instead, it exists as a resonance hybrid, a single, stable structure that is a blend of both possibilities. This modern view explains why all carbon-carbon bonds in benzene are identical. They are neither single nor double bonds, but something in between. As you can see in the final model, the circle inside the hexagon represents a cloud of delocalized electrons shared equally among all 6 carbons. This delocalization gives benzene its exceptional stability. Experimental evidence confirms this. Every carbon-carbon bond in benzene measures exactly 1.39 angstroms, a perfect intermediate length that proves the bonds are identical, from Faraday's initial discovery to Hückel's ring structure, and finally to Pauling's resonance hybrid. Our understanding of benzene has grown from a simple formula to a sophisticated model of electron delocalization. This evolution highlights how scientific knowledge builds upon itself, refining our view of the molecular world. Aromaticity and Hückel's rule, the golden key that unlocks why some ring-shaped molecules are exceptionally stable, while others are not. To be classified as aromatic, a molecule must satisfy 4 essential criteria, all of them non-negotiable. First, it must be cyclic, meaning it forms a closed ring structure. No open chains allowed. Second, it must be planar, perfectly flat. All atoms in the ring must lie in the same plane so that their p orbitals can overlap effectively. Third, it must be fully conjugated. Every atom in the ring must have a p orbital, allowing electrons to delocalize across the entire system. This creates a continuous cloud of pi electrons above and below the ring. And fourth, the most famous rule of all, it must contain 4n plus 2 pi electrons, where n is any whole number, 0, 1, 2, 3, and so on. Let's see how this works with benzene, the classic example. Benzene has 6 pi electrons. Plug into the formula, 4 times 1 plus 2 equals 6. So n1, that satisfies Hückel's rule. And since benzene also meets the other 3 conditions, cyclic, planar, and conjugated, it is definitively aromatic. Its stability, exceptional. Now look at the diagram on the left, the star-like polygon, labeled 4n plus 2. The numbers around it, 2, 6, 10, 14, represent the magic electron counts that confer aromaticity. For n0, you get 2 pi electrons. For n1, 6. For n2, 10. For n3, 14. These are the only electron counts that create aromatic systems. But what happens when a molecule doesn't follow this rule? Consider cyclobutadiene, a 4-membered ring with 4 pi electrons. 4 fits the pattern 4n, where n1. Molecules with 4n pi electrons are called anti-aromatic. They're not just unstable. They're highly reactive and often difficult to isolate. Cyclobutadiene distorts out of planarity to avoid this instability, but if forced to stay flat, it becomes dangerously unstable. Then there's cyclooctadiene, an 8-membered ring with 8 pi electrons. 8 is also a 4n number, n or 2, so you might expect it to be anti-aromatic. But here's the twist. Cyclooctadiene avoids being planar. It adopts a tub-shaped conformation, breaking the planarity requirement. Because it's not planar, it's neither aromatic nor anti-aromatic, it's non-aromatic. Non-aromatic compounds behave like normal alkenes. No special stability, no unusual reactivity. So let's summarize using the table. Benzene, 6 pi electrons, aromatic, stable. Cyclobutadiene, 4 pi electrons, anti-aromatic, unstable. Cyclooctadiene, 8 pi electrons, non-aromatic, neutral stability. This framework, Hückel's rule combined with structural requirements, allows chemists to predict whether a ring system will be unusually stable, unusually unstable, or just ordinary. Benzene geometry and hybridization details. Let's begin with the structure you see on the left. A perfect hexagon of 6 carbon atoms. each bonded to one hydrogen atom. Every internal angle, every CCC bond angle, measures exactly 120 degrees. This isn't arbitrary. It's the geometric signature of sp2 hybridization. Each carbon atom in benzene undergoes sp2 hybridization. That means it mixes one s orbital and two p orbitals to form three identical sp2 hybrid orbitals, arranged in a trigonal planar, geometry 120 degrees apart. These three sp2 orbitals form sigma bonds, two with neighboring carbons and one with a hydrogen atom. All 12 atoms, 6 carbons and 6 hydrogens, lie perfectly flat in the same plane. Benzene is not just roughly flat, it is rigorously planar. But here's the key. Each carbon still has one unhybridized p orbital left over, perpendicular to the plane of the ring. These 6 p orbitals don't stay isolated. They overlap sideways with their neighbors above and below the ring, forming a continuous, donut-shaped cloud of electron density. This is the delocalized pi system, often drawn as a circle inside the hexagon. Look at the diagram on the right. It shows a single carbon atom with its 3 sp2 hybrid orbitals lying in a plane, and 2 lobes of the p orbital sticking out, one above, one below. In benzene, all 6 carbons do this, simultaneously, creating a seamless ring of overlapping p orbitals. The result? A torus-shaped electron cloud enveloping the entire molecule, visible in the bottom right illustration as those glowing blue rings surrounding the hexagon. Now let's talk about bond lengths, because they tell us something profound. In typical organic molecules, a carbon-carbon single bond measures 1.54 angstroms. A carbon-carbon double bond measures 1.34 angstroms. But in benzene, every carbon-carbon bond is identical and measures precisely 1.39 angstroms. Not halfway between single and double, but closer to double, yet uniformly distributed. This uniformity is experimental, proof that benzene does not have alternating single and double bonds. If it did, we'd measure 3 short bonds, 134 O, and 3 long bonds, 154 O. But we don't. We measure 6 identical bonds, all 139 O. Why? Because the electrons are delocalized. Each bond shares partial double bond character due to resonance. The true structure is a hybrid, an average of 2 contributing Hückel structures, resulting in equal bond lengths and extraordinary stability. So what does this mean for chemistry? It means benzene doesn't behave like alkenes. It resists addition reactions that would break the aromatic system. Instead, it prefers substitution reactions, preserving the precious delocalized pi cloud. The geometry dictates the behavior. The hybridization enables the delocalization, and the delocalization grants the stability. Electrophilic aromatic substitution, EAS, mechanism, the cornerstone, reaction that allows us to functionalize benzene rings while preserving their precious aromatic stability. Unlike alkenes, which readily undergo addition reactions, benzene resists them because breaking its delocalized pi system would cost too much energy. Instead, benzene prefers substitution. It swaps one of its hydrogens for an electrophile, but only through a carefully choreographed, 3-step dance that temporarily sacrifices, then restores aromaticity. Let's walk through each step using bromination as our example, where benzene reacts with Br2 in the presence of Phe-Br3 to form bromobenzene. Step 1. Electrophile generation. Benzene itself is not reactive enough to attack neutral Br2, so we need help, a Lewis acid catalyst like Phe-Br3. The iron accepts a pair of electrons from one bromine atom, polarizing the Br-Br bond and generating a powerful electrophil, the bromonium ion, Br+. The counterion formed is Phe-Br4. This activated electrophile is now ready to be attacked by benzene's electron-rich ring. Step 2. Benzene attacks the electrophile, forming the sigma complex. Now comes the critical moment. The pi electrons of benzene, those beautifully delocalized electrons above and below the ring, act as a nucleophile. They attack the positively charged Br+, forming a new carbon-bromine sigma bond. But here's the catch. When one carbon forms this new bond, it changes hybridization from sp2 to sp3. That breaks the conjugation. The positive charge doesn't stay on that one carbon. It gets delocalized over two adjacent carbons via resonance, creating what's called the sigma complex or arenium ion. This intermediate is a carbocation, unstable, high energy, and crucially, non-aromatic. The beautiful ring of delocalized electrons is broken. This step is slow. It has the highest activation energy. On the energy diagram you see on the right, this corresponds to the first peak. TS1, transition state 1. The sigma complex sits in the valley between TS1 and TS2, a local minimum, but still higher in energy than both reactants and products. Step 3, base removes H+, restoring aromaticity. The final step is fast and driven by thermodynamics. A base, often the Phe-4 ion generated in step 1, or sometimes OH, if present, removes the proton, H+, from the sp3 carbon that originally held the hydrogen. When that proton leaves, the carbon reverts back to sp2 hybridization. Its p orbital rejoins the system. The two electrons from the CH bond flow back into the ring, restoring the full cycle of 6 delocalized pi electrons. Aromaticity is restored, and with it, massive stabilization energy, approximately 36 kcal/mole, is regained. This restoration of aromaticity is the driving force behind the entire reaction. It's why EAS happens at all. Nature favors returning to that low energy, highly stable aromatic state. Benzene derivatives, naming and applications, where we explore how substituents change benzene's name, structure, and real-world impact. First, substitution patterns. When two groups attach to the ring, their positions matter. Ortho is 1-2, adjacent carbons. Meta 1-3, separated by one carbon. Para 1-4, opposite each other. These terms are used alongside IUPAC numbering to precisely describe disubstituted benzenes. Next, common derivatives. Everyday molecules built on the benzene core. Toluene, methyl group attached, used in solvents and explosives. Phenol, hydroxyl group, key in disinfectants and plastics. Aniline, amino group, essential for dyes and polyurethanes. Benzoic acid, carboxyl group, common food preservative. Finally, industrial and pharmaceutical applications. Benzene is not just a lab curiosity, it's an industrial workhorse. From benzene, ethylbenzene, styrene, polystyrene, a plastic, or via cumene process, benzene, phenol, plus acetone, nylon 6,6 synthesis. And in medicine, meet aspirin, derived from salicylic acid, which itself comes from phenol. Its structure, a benzene ring with acetyl and carboxylic acid groups, ortho to each other. From naming rules to life-saving drugs and everyday plastics, benzene, derivatives shape our world. Benzene summary, misconceptions, and safety. Your final checkpoint for mastering benzene: what it is, what it isn't, and why you must handle it with care. Let's begin with the 8-point checklist. Everything you need to remember about benzene. Molecular formula, C6H6. All carbons are sp2 hybridized. Perfectly planar hexagon with 120-degree bond angles. Delocalized p electrons forming a ring above and below the plane. Aromatic by Hückel's rule, 4n+2. Electrons. That's 6 when n equals 1. Undergoes electrophilic aromatic substitution, not addition reactions. Stabilized by resonance, gaining approximately 36 kilocalories per mole of energy. And critically, carcinogenic. Benzene is a known human carcinogen. Now, let's clear up common misconceptions. Wrong. Benzene has alternating single and double bonds. Correct. All carbon-carbon bonds are identical. Measuring 1.39 angstroms due to electron delocalization. Wrong. Benzene undergoes addition reactions like alkenes. Correct. It prefers substitution to preserve its precious aromatic stability. Wrong. Benzene is saturated. Correct. It's unsaturated, but unusually stable thanks to resonance. Wrong. Double bonds are localized between two atoms. Correct. Pi electrons form a continuous cloud, delocalized over all 6 carbons. And now, the most important part, safety warning. Benzene is classified as a Group 1 carcinogen, meaning it causes cancer in humans, particularly leukemia. Always use it under a fume hood. Never inhale vapors. Handle with gloves, goggles, and proper ventilation. Final insight? Benzene's extraordinary. Stability, born from electron, delocalization, doesn't just make it chemically unique. It defines the entire field of aromatic chemistry. From pharmaceuticals to plastics, its influence is everywhere, but so is its danger. Respect its power. Understand its structure. Handle it safely. Thank you for completing this summary on benzene knowledge that protects both your understanding and your health. If you found this video helpful, please give it a thumbs up. It really helps our channel grow. Don't forget to share it with classmates or anyone studying organic chemistry. Drop a comment below. Tell us which topic you'd like us to cover next, or ask any questions you still have about benzene or aromaticity.